Okay, so I left you with this question about why Mars might no longer have a magnetic field. And the key point here really is that it's somewhat smaller than the Earth. And because it's smaller, the sort of it will have had a molten iron core in the past, which is why it used to have a magnetic field, we believe, and there's plenty of evidence for that. You can find residual magnetism in the rocks on Mars. But because it's smaller, the planet will have cooled down more vigorously than the Earth, so it'll cool down faster than the Earth, and so the crust has long since solidified, so it's now got a very thick crust, and seems to be no significant liquid underneath there now. Again, plenty of geological evidence for a lot of volcanic activity in the past on Mars. So clearly there was molten material in Mars previously, but no longer. So, it may have solidified after a billion or so years and the magnetic field disappeared. And so basically Mars does not have the protection of a magnetic field anymore like we do on the Earth. So the charged particles from the sun can now penetrate the thin atmosphere quite readily. And actually the solar wind contributes to removing some of Mars' atmosphere over time as well. And so basically if you're too small as a planet, you're not going to be able to sustain that magnetic field, and that probably a key factor in the development of life. Okay, so back to characterizing our planets, now using the parameters of its radio emission. So the first thing that is very distinctive about this characteristic sort of shape of the spectrum from Jupiter and from any sort of planetary interaction with the solar wind is this cutoff in frequency here. So the frequency of this cutoff actually tells us the strength of the magnetic field on the planet. Okay, so if the magnetic field was stronger, then this cutoff would move to higher frequencies. And so it's kind of intriguing, actually. The cutoff of Jupiter is here at about 40 megahertz. The lowest frequency that the low frequency part of the SK is going to observe at is 50 megahertz. So basically the SK would not be able to detect sort of Jupiter-like emission because it would the strong part of the emission is just below its frequency cutoff. But any planets with a slightly stronger field will easily be in the range of SK low. So in principle here, there's a way of measuring the strength of the magnetic field by looking for that cutoff in the spectrum. So then these are a little bit complicated, but I showed you these dynamic spectra again, time versus frequency, so plotted that way around. Also looking at so this is the intensity, but here is just the circularly polarized emission on this diagram. So these are models by Hess and Zarka of how you could diagnose different parameters from the characteristics of the dynamic spectra of both the intensity and the circularly polarized radio waves from any such systems. So this is like looking ahead to what we might be able to do. So one thing you can certainly do is find out the rotation period of the planet itself. Okay, so you'd be able to find out how fast it was rotating, because the period here would be exactly the one period of rotation of the planet, because those auroral spots will rotate with the planetary rotation. So that should be fairly obvious in the dynamic spectra, but it's not the only thing. the inclination of the orbit to the star, or the orbital plane to the star, would also change the dynamic spectra, and so you should be able to diagnose the orbital inclination as well. So, so it doesn't have to be a transiting planet or anything like that. Any inclination, you should be able to see the radio emission, and that also deduce the inclination, which is key if you're trying to measure accurately the mass of the planet. You need to know the inclination of the orbit. And as we see for quite a lot of magnetic bodies, the magnetic axis does not need to be aligned to the rotation axis. I mean, on the Earth, it's a little bit off. The magnetic North Pole is not the same as the rotational North Pole. And that will show different patterns in both the intensity and polarized light. Again, the details don't matter too much here. Just this idea that we can diagnose a lot of information about these planets through the nature of this low frequency radio emission. So there's another mechanism that is so you observe the same way, but it's actually generated slightly differently, and that's analogous to the situation where we had with Io, the moon of Jupiter, and Jupiter itself, where the orbit of the body, like a magnetic body around the bigger magnetic object, they get connected by magnetic flux tubes, and then this can cause aurorae on the bigger body. So if this was Io, this would be Jupiter. That's what happens. That's what's responsible for some of the aurorae on Jupiter, rather than just the stellar wind or the solar wind coming in. Okay, so there's two components to Jupiter's emission. So this can actually happen if you've got magnetic planets orbiting a magnetic star, and most stars are magnetic. So you end up generating the aurora on the star rather than on the planet. And so electrons will hurtle along here and spiral into the magnetic field in the upper atmosphere of the star and generate aurorae there. And so you get radio emission this way. So this is what's referred to as a star-planet interaction. And again, stars much smaller than the sun are more convective and more magnetically active. And so we might expect to see this in these systems. And so the jury is still a little bit out on this, but it looks like we're now moving into the era of the radio detection of extrasolar planets. So there's a couple of discoveries here in the last year that look very much like this kind of star-planet interaction mechanism. So the first one here was observed with the so-called LOFAR telescope, which operates at very low frequencies and is based in Europe and centered in the Netherlands. And here we can see two radio images of the same piece of sky, but here there's a bright source and here it's disappeared. Okay, and the position of this source corresponds to a nearby low mass star. And the little inset here is the image in circularly polarized radiation. And you can see that when the object is detected, it's very strongly circularly polarized. So that is consistent with this star-planet interaction mechanism. And so that, and it, so this emission was highly variable and circularly polarized. And this was then followed up to look even harder to see if a planet could be found around this particular star. And indeed, this is now the radial velocity curve of that star. And it shows indeed that there is a planet here with a 2-hour orbit. Sorry, a 2-day orbit, I think. And that was consistent with the kind of parameters that we needed to explain this kind of star-planet interaction. So that looks like it's becoming consistent, and obviously this object is going to be followed up with many more studies to try and confirm and characterize this radio emission and confirm that it's from the planet interacting with the star. And then another very interesting observation, again, very recently, with actually the closest star to us, Proxima Centauri. So this is Proxima Centauri itself is a companion to Alpha Centauri, a very, very bright sun-like star, which is just over a parsec away from us. Proxima Centauri is even closer, in a wide binary orbit, and was already known from radial velocity studies to have a planet, Proxima Centauri b, in orbit around it. And so recently, emission at actually fairly high frequencies. So this is just standard frequencies, the frequencies that Meerkat is operating at. This was done with the Australia telescope. And we can see variable strength radio emission, and the locations of the peaks of these emission are consistent with particular locations in the orbit when you would expect to see strong radio emission. And again, this radio emission is highly circularly polarized. This is the V Stokes parameter that was mentioned before. So this is circular polarization. And you can see that the emission is circularly polarized and also switches direction. So again, that is also important. So at one point, the cone of emission is pointing towards us, and then in the other part of the orbit, the cone of emission is pointing away from us. So that again is very consistent with what we expect for this kind of mechanism of star-planet interaction. So this all looks promising, and of course will be closely followed up. So it looks like we're entering a new era of radio detections of extrasolar planets. But I just want to finish up on this topic, since I don't think it should be left out, which is SETI, or the search for extraterrestrial intelligence. So now we're not talking about looking for planets that are in the habitable zone and might have a nice magnetic field and a nice rocky composition, and maybe a nice thick atmosphere. Can we actually go out there and directly look for intelligent life? And the way that the idea is that you do this in the radio regime, because here on Earth, we use radio wave signals for our communications and our navigation, so radar, etc., etc. So this is the idea of actually looking for non-natural radio signals. So non-natural usually means very narrow band. So a lot of the radio communications done here on the Earth are done with incredibly narrow bandwidths. Okay. And in fact, they're so narrow, they would be narrower than any sort of, normal spectral line. So they can't be mistaken for like a spectral line emission, because they're just so narrow. And of course, we also modulate them with time and frequency in order to convey the information on the radio band carrier. So you're looking for usually narrowband signals modulated in time or frequency. And this spectrum here shows you kind of the cosmic background of radiation. I think Mark showed this a bit earlier. And so again, if you want to communicate over kind of interstellar distances, then it's also a good place to do it, because it's the quietest, if you like. There's the background is the quietest. And really, for the first time, once the full SK is up and running, we will have the sensitivity to really start to look for sort of interesting levels of any radio communications coming from other planetary systems. And that's because the SK will have the sensitivity to detect, in a sense, the kind of signals that we generate here on the Earth every day, and have been leaking out of the Earth for the last 70 or 80 years. And so, anyone anywhere else with a telescope as sensitive as the SK would be able to pick up our communications if they were within 70 light years of us. And so, let's try that experiment the other way around. We're building the SK. It's going to have the sensitivity to pick up things like just normal airport radar, as indicated by this schematic here. And so, the SK operating across all these different frequencies should be able to pick up those kind of signals, of course, if they exist. Now, that's a massive if. And, even if there is life somewhere else in our galaxy, the chances of it being, within a few hundred light years might be quite small. Could be extremely small, could be zero. That's the fun with SETI. You don't know until you look. But of course, if something is found, then that has profound implications for us here on the Earth. Okay, so that was, and SETI is now an integral part of the SK science case, and the Meerkat telescope is already in partnership with the Breakthrough Listen project, which is a privately funded project to look for SETI signals. And so, this kind of thing is already underway with Meerkat, and the same thing will happen with the SKA. So, and of course, this goes hand in hand with the, this incredible discovery that all stars basically have planetary systems anyway. And so there's lots of, sensible targets to look at now. So we can try and target systems that have Earth-like planets in the habitable zone. We could try and target other stars that are like the sun. And we could just target all nearby stars if we wanted to. Okay, so again, this idea of just doing a volume of space. If we think that all stars have planets, then let's just search all of them deeply for any sign of non-natural signals. So that's pretty exciting stuff, and a good place to finish up. So, so I would just summarize by saying that, even though most planet detection and characterization has so far been carried out in the optical and the infrared, the sensitivity, especially of the SKA, will allow radio observations to really contribute to this field and make unique insights again into the sort of magnetic fields of exoplanets, which will tell us about, their interiors, the surrounding plasma environment, and various characteristics of their orbital and rotational motion. And of course, we have this possibility to keep searching for signs of intelligent life to answer the question of whether we are alone in the universe. Okay, so that brings us to the end of the lectures in this unit. So I will stop there and hope you've enjoyed the journey.